All right, gather round. We're going to spend a little bit of time talking about aircraft instruments. Now, before we get started, aircraft instruments can be divided roughly into a couple different categories. We have pressure indicating equipment, temperature indicating equipment, we have mechanical indicating equipment, and gyro indicating equipment, or Euro equipment if you like Greek food. Anyway, carrying on, let's take a look at pressure sensing equipment. So, starting right off, we have in front of us a mercury barometer. This is a very basic example of an absolute pressure measuring gauge. We say absolute pressure because absolute pressure measures a reference pressure to a vacuum. The way that works in a mercury barometer like this is we fill this column with mercury. Mercury obviously is pretty dense, it has some weight, and it's upended into a pool of additional mercury. And as the mercury falls down that tube, we're going to we're going to create a vacuum in the space just above, which makes some sense. And as the atmospheric pressure or the weight of the column of air, right? Remember, we are living within an atmosphere. So above you, there is thousands of feet of air that is pressing down on you at all times. That's what we refer to as atmospheric pressure. At sea level, it's about 29.92 inches on a standard day. However, as we start to get higher and higher, that is going to change. The reason we refer to this in inches is because we're talking about inches of mercury in a mercury barometer. Even if we were using equipment that does not use mercury in it, we still refer to it as inches of absolute pressure. That is our reference point because realistically, the mercury barometer is the most accurate. So what ends up happening is as our atmospheric pressure increases, the density increases, it's going to force the mercury to go up this tube and push into that vacuum. On the other hand, as our atmospheric pressure decreases, the mercury is going to go down the tube and we're going to increase the pull of that vacuum. That is how we measure absolute pressure against a vacuum. A way that we can do that in an instrument is by using an aneroid barometer. Now, an aneroid, in case you aren't familiar with this before, is basically just a metal, we'll call it a crinkly corrugated disc. This part right here, our aneroid, which has a vacuum inside of it. So this metal chamber is created, and the last thing that's done is all of the air is sucked out of it, and then it's sealed. And you can probably go into the Latin roots of the word, but typically when you see something like "an," that's going to be negative or non. Anyway, we're in the Latin class, but that's the idea. The aneroid is a vacuum chamber. So when we measure our reference pressure, we have a spring that's calibrated along with our pointer that works on something like, say, an altimeter or a manifold pressure gauge, any number of things. And it is connected to this aneroid. So what ends up happening as our pressure increases, the atmospheric pressure, this aneroid is exposed to atmospheric pressure. As it increases, it's going to squeeze that aneroid in because we have a vacuum inside. As a result, it's going to move this arm right here, which turns this gear, which is going to change where our pointer points. On the other hand, as atmospheric pressure starts to decrease, then this aneroid chamber is going to be able to expand slightly, and it's going to change the indication we have on our needle. Very, very simple system. Now, looking at a cross section of that, this is what it would look like if we were looking at the inside of our aneroid. So effectively, the reason this is corrugated, if it wasn't, then it would just collapse. So this corrugated motion adds a little structure and it also helps it to spring a little bit. So as you can see right here, inside is where our vacuum would be, right? But the atmospheric pressure is going to push in against that vacuum. The spring action will fight against it. As we start to relieve atmospheric pressure, that spring action will force back out against the vacuum and the aneroid changes shape. Very, very simple. What we'd look at right here is an altimeter that would use that. So a standard pressure altimeter, it displays absolute pressure. And over here on this right side is something referred to as a Colesman window. This Colesman window allows us to adjust for prevailing atmospheric conditions at sea level. So if this makes any sense, let's try to draw this out. So if I'm flying an aircraft, I need this to indicate accurately. Now, most altimeters like this are going to display in feet above sea level. So that is our reference level. So for instance, at Payne Field, we're about 606 feet above sea level. However, if you were flying to the airport or you were planning on taking off from the airport and you listen to the automated weather indicating service that we have, the ATIS, it's going to tell you what the prevailing atmospheric pressure is. And the reason that's important is depending on the temperature, depending on the time of year, our barometric pressure is going to go a little bit up or a little bit down. So, for instance, if this is, let's go for something that makes sense as a color. Let's go for blue. So if my sea level right here is my reference, and let's say I'm at 29.9 inches of mercury, right? 29.92, that's going to be our standard day. So 29.92, that's our standard day at sea level. So if I am significantly higher, right? If I'm flying up over the mountains, I'm way up here at altitude at, let's say, 10,000 feet ASL or above sea level, then that is referenced from that sea level. However, if the barometric pressure changes, so if it's a particularly warm day and we have a higher barometric pressure, then if I have my altimeter set to a standard barometric pressure at sea level, it's going to throw off my indication. It's not going to make any sense. So we need that to be accurate. That's why we can adjust the Colesman window, which adjusts the calibration of our altimeter by turning this knob right here. So in most cases, we can call the ATIS, we can get what our barometric pressure is for that day, and we can set the altimeter to that. On the flip side, if you're at an airport and you happen to know the elevation, but you don't know the barometric pressure, then we can work backwards. So for instance, if I know the elevation at Payne Field is 606 feet, then I can set my altimeter until it indicates 606 feet, which the way that works, by the way, it's a little bit like a clock. It has three hands, but they're a little bit different. So the big hand right here is going to indicate in hundreds of feet. This middle size hand is going to indicate in thousands of feet. And our very small hand is going to indicate in 10,000s of feet. Now, if you are in a smaller aircraft, you may not have a 10,000 foot indicator on that aircraft because it can't fly that high, but that's really neither here nor there. So if I was setting at Payne Field, I would turn it until my large hand right here was just past the 6, indicating just beyond 606 feet, and I could see what my barometric pressure is in the Colesman window. So we can work backwards that way as well. Just a little bit of background information on what this looks like to a pilot, or if you happen to be messing around with one of these in a hangar. All right, next we're going to look at a different kind of indicating pressure, and this is gauge pressure. Now, this may be a little bit of review from engine instruments, but gauge pressure references pressure within a sealed system against atmospheric pressure. That's key to know. So that does potentially change if we change our altitude. And so usually the equipment that we use for gauge pressure is going to be a little less sensitive. In this case, the Borden tube is something that we would commonly see used with oil pressure. And effectively what you see is the Borden tube itself is this half moon shaped flat tube. And the idea of this is it has a little bit of spring action because it's metal. But what happens is as we push pressurized liquid, let's say oil, into this Borden tube, it's going to have the tendency to want to straighten out this tube. So it's going to try to flatten out that tube. You can kind of picture if you've ever used one of those little party favor kazoo things where you blow into it and the little streamer rolls out. It's kind of the same concept. As we increase pressure, it's going to try to straighten out that Borden tube, which by means of this linkage right here, as it starts to try to straighten out, it's going to move this gear, which in turn rotates our indicating gear or the pinion on the face of the gauge. So this is how a basic Borden tube would work. And like I said, typically you would see this with something like oil pressure, a few other indications like that. Next, we're going to take a look at a differential pressure gauge using a bellows. So in this case, we have a bellows that's going to be used for lower gauge pressure. So we wouldn't be using this for anything like a high pressure system. This would typically be used for something like maybe a vacuum gauge or a lower pressure indicating system. And what you'll see here is that we have our linkage right here. It looks very much like an aneroid, but the difference is it has not been evacuated and sealed to hold a vacuum inside. If you look on the other side, there's actually a tube that goes into the bellows. So we are providing pressure directly into that bellows, but the rest of this works basically the same. So we have the same cross section, the same spring action with these corrugations here on the bellows. And what will happen is as we introduce pressure into that bellows, it's going to expand just like the aneroid would, except instead of because of a drop of atmospheric pressure around it, it's going to be due to pressure being sent into our bellows, and it's going to move this linkage out, and as a result, it's going to move our sector, and it will move the pinion to change the needle indication. So that's a bellows. All right, let's take a look at a different kind of gauge. So we'll see how this works in practice. So that bellows, we can see that that was measuring the difference between atmospheric pressure and pressure inside the bellows. Those are the two forces that are fighting. In this case, we're going to take a look at an airspeed indicator. Now, an airspeed indicator is a true differential pressure gauge. And the way that this works is obviously as we change altitude, we're going to change density of the air. And an airspeed indicator measures two things. It measures the pressure of static air around the aircraft, but it also measures ram air coming into what we call a pitot tube at the front of the aircraft. So it measures the pressure of air. Basically, as the aircraft increases in speed, the amount of pressure in that pitot tube is going to increase and get higher and higher. That pitot tube feeds into a bellows, just like we saw in the last slide. However, as we get higher in altitude, that density is going to change. So theoretically, if I was climbing at the same rate of speed as my altitude increased, if I only measured my pitot pressure, then I would actually notice my airspeed slowly declining over time. It would look like the aircraft was going slower and slower, not because it was necessarily flying slower, but because the pressure that's being rammed into that pitot tube is less and less as the atmospheric pressure gets lower and lower. So as a result, we need something a little more accurate, and that's what differential pressure can do for us. So the static connection is measuring the static pressure around the aircraft. Typically, it's going to be located somewhere on the aircraft where we don't get any ram pressure. It could be on the pitot tube itself. It could be static ports that are located on the side of the fuselage. Typically somewhere where they won't be disturbed by airflow. But it basically measures the ambient pressure around the aircraft and uses that as an additional reference. So our static pressure is going to dwell just inside the instrument here, and then our pitot pressure goes directly into the bellows. So those two forces are going to act against each other. As the pitot pressure increases relative to the static pressure, then that bellows will expand and we change our indication. As the pitot pressure drops relative to our static pressure, then that bellows will start to contract and we get a different reading. So that's how a differential pressure gauge works for us. All right, another version of a differential pressure gauge. We saw basically just a little bellows inside that airspeed indicator. In this case, we could be taking a look at a reference bellows. So it does fundamentally the same job, except instead of filling the entire case of the instrument with a specific pressure of air, we actually force that into one side of a bellows, and our other reference pressure is going to come into the other side of the bellows. And what's going to happen is as these two force against each other, if they're in equilibrium, then this mechanical arm is going to stay in the middle because our two pressures against each other are equalized, right? However, as one pressure starts to increase, and the other stays the same or drops, it's going to force this arm to displace just a little bit. And that's how we get it to move our sector and pinion and change the indication. And the nice thing with this is we can use it for a number of different kinds of instruments. It could be for absolute pressure. So one side could be hooked up to a vacuum. It could be used for differential pressures, or it could be used for gauge pressure. So one side could just have atmospheric pressure and the other side could have whatever we're referencing. So we have a lot of versatility with this kind of double acting bellows where you have a reference side and a measuring side. All right, that's enough of pressure equipments. We're going to talk about temperature indicating equipment. So as we talk about temperature indicating equipment, good old thermometers, we'll look at our basic mechanical thermometer. So this is a standard bimetallic thermometer. What we mean by bimetallic is it's kind of weird, but if you can picture, we have a metallic spring which is out here on the measuring end. So in the probe, this is a free air gauge. So this will be the part that's sticking outside the aircraft to actually measure the temperature. So this bimetallic spring, the way that it works is we're able to use basically differential coefficients of expansion for two different metals. And so the way that works, if we have one strip of metal that's coiled into a spring like that. It's not a well-drawn spring, but it's a spring nonetheless. And then we fuse another piece of metal onto that strip right there. Again, not a great drawing. What's going to happen is as the temperature changes that affects this bimetallic strip, one side, let's say the blue side, is going to expand more quickly than the black side right here. And as a result, it's going to cause this entire spring to try to straighten out a little bit. So instead of being curved like that, it's going to cause it to try to straighten out, which is going to turn our needle. On the flip side, as it starts to get cooler and cooler, the difference in the change of expansion is going to cause it to contract and get tighter, which will change it in the other way. It's a very, very basic system. It's not necessarily the most accurate because it can take a little bit to indicate changes in temperature, but it works totally fine for something like a free air gauge because the temperatures aren't so hot that it's going to damage the bimetallic spring. And on top of that, usually our rate of change for air temperature isn't going to be fast enough where a little bit of lag time doesn't really hurt. And the plus side is we don't need to have it powered by anything. It just indicates, so it works. But that's the basic fundamental behind it. We're going to get a little more complex though. A resistance bulb is a different kind of temperature measuring device. And the idea is it acts as a circuit. So if you look on our input here where the AIN connector is, we have power in and we have power out. So we have a positive and a ground side to this bulb. And effectively, this entire bulb works as a variable resistor. So the way this works is as the temperature changes, we have conductors that send it to this mica core, this nickel winding on the mica core. And what's going to happen is as the temperature changes, it's going to cause the contact within that bulb to change a little bit. So we'll either have more air gap or less air gap, and it's going to change the amount of resistance being sent through this bulb as current gets sent through it. Now, the reason that's important is what we'll see on our next gauge. This is a Wheatstone bridge. This is a very basic device that we use to measure temperature. And effectively, it's all going to change based on the current flowing through it. Remember, when we start having things like parallel electrical paths, our current is going to remain the same. So if up at our input here, I have 12 volts DC going into the Wheatstone bridge, the expectation is we'll have a voltage drop because of the resistors, but it's not going to change fundamentally. So at this point, we should be sending the same voltage in both directions down each leg of this Wheatstone bridge. Now what you're looking at is the indicator in a equilibrium state. So that means that when our indicator points straight up like this, the resistance path going down this leg and this leg are the same. Now this is kind of interesting because resistor 1 and resistor 3 act as a reference for this bridge. However, resistor 2 and the bulb are the varying parts. So we just talked about how that bulb is a variable resistor. So in equilibrium, this is going to be exactly as it is. However, as our bulb changes resistance, it's going to change the amount of current that flows down this leg of the Wheatstone bridge as opposed to this side of the Wheatstone bridge. And so we have, let's say, a needle here that's a permanent magnet. So these coils on either side are going to produce a magnetic field. So as our current flow down this side increases, the magnetic force is going to increase, and as a result, our needle is going to start to deflect that direction. However, on the other side, as we start to increase resistance, if our current flow starts to have an easier time going down this path and the current flow increases and has a harder time going down our bulb path, it's going to cause this needle to deflect that way. Very simple system, but it works very, very well. Let's take a look at a modification of that, right? So instead of just resistors, in this case, we've created two coils. And what we're looking at here is what we call a moving coil ratiometer. The reason we call it moving coil is because the part attached to the needle that moves is not a permanent magnet. The permanent magnet is actually built into the housing. And so the way this works with our moving coil is that as we change the amount of current flow through either side of this coil, one goes to the bulb and one, so we see right here, this side goes to our bulb with a variable resistor. This side is going to go through our reference side, through the reference resistor, right? But the principle is the same. So as current increases on the coil one side, it's going to force the needle to deflect that direction. However, as current flow slows down on this side and starts to increase on the coil 2 side, it's going to cause the needle to deflect that way. Because we have a permanent magnet, the coil is going to change the strength of the magnetic field on either side of that needle, and it's going to move back and forth. The nice thing about these is they tend to have a much better rate of change to indicate than just a traditional Wheatstone bridge with a permanent magnet needle. So that's what we see with that. This is going to be an even more complex version of this, but in this case, we have two fixed coils. So this is a moving magnet ratiometer. In this case, we do have a permanent magnet on our needle, but we have two coils on either side. Now, the difference with this is you'll notice we have multiple paths to flow through. It's a little more complex than the basic Wheatstone bridge that we saw. So in this case, we have a current leg flowing this way, and we have a current leg flowing this way. You'll notice the coil is something kind of weird going on, right? So we flow through this resistance leg. We have an additional resistor on the high end coil, and we have our bulb over here. I'm not going to get you too far into the electrics of this, but effectively try to keep in mind this is doing the same job as the basic Wheatstone bridge that we just saw earlier. So effectively current enters in through this branch point, right? And it's going to flow through the low end coil and the high end coil. Now, the reason that this is designed the way it is if we have a permanent magnet here in the center, right? If we need the magnet to deflect to the right, that means we need the north side of the magnet to be attracted to the right-hand side of the gauge, we'll say. But if we need the needle to deflect the other way, the north side has to be attracted to the left side of the gauge. That's important because the design of this entire bridge is going to allow the coils to reverse polarity. And that's why you see these paths attached the way they are. Effectively, they're designed so that current can reverse its flow through those coils and change the polarity of the coil. That's important because we need it to be able to reverse polarity for the magnet to go one way or the other. Typically, when you look at a temperature gauge like this, when the power is shut off, master shut off, there's nothing flowing through the gauge, it's typically going to go to a neutral position, which that depends what temperature it's going to be, depends on how high the gauge goes, but it's going to pop into a neutral position until it's acted on by a magnetic field. So that's what we're looking at with our ratiometers. Last thing we're going to look at for temperature indicating gauge is our thermocouples. Thermocouples are used for measuring much higher temperature applications. We're going to see this used in things like cylinder head temperatures. We're going to see it with EGTs or exhaust gas temperatures, both in reciprocating engines and in turbine engines. And obviously, the requirements for this are going to change depending upon what our application is. Turbine engines are going to operate at much higher temperatures. As a result, the thermocouples that we use must be much more robust. That's not a sentence I'm going to try to say again anytime soon. With this particular installation, again, we're talking about dissimilar current flow. This is a current measuring device. We're talking about dissimilar current flow through each one of these wires. Each wire is going to be made of a different kind of metal, and that is going to change how current flows through it. The one thing that I really want to point out with these from a service standpoint is when you get a thermocouple set, it is designed as a set, which means you cannot swap it with other thermocouple components, and you also cannot change the length. So we have connectors that are going to be in the middle of our connection so that we can remove the engine if we need to without pulling out the entire instrument. However, if that thermocouple, for instance, wasn't long enough, we cannot just splice in additional wire to try to extend the length. It's now going to change the resistance potential of that entire lead, and it's going to throw off our temperature indicating. On the other hand, right, if we break the end, say we snap off a thermocouple, we've seen those little spark plug gasket replacement thermocouples. If we break that off, then we're going to have to replace the entire lead. So we can't just splice things in, otherwise it won't measure accurately anymore. Another version of this we see, we had that little spark plug type that goes right underneath the spark plug where the gasket normally would. It's made out of copper. We also have a bayonet style. So you may see holes on a cylinder head on a reciprocating engine. that you think, oh, are we missing a fuel injector or something like that? No, it's not a fuel injector. It's a place for a bayonet to go into. And so we have a threaded portion right here. We have our measuring junction with the spring that gets pushed in, and that spring force is going to keep this measuring junction pressed against the cylinder head itself. The nice thing about these is they press in further in towards the cylinder head. We don't have issues of cooling air blowing over the spark plugs or anything like that. So we can actually tend to get more accurate measurements on our CHTs using bayonet style thermocouples than we would with the gasket style. As we get more complex, we're just looking at the actual materials of this thermocouple. So in this case, we have two sides. We have a positive and a negative side. With the lower temperature, I shouldn't say lower temperature, for the exhaust gas temperature leads, we're typically going to use chromel and alumel, which are just two different alloys that are going to be able to work with those temperatures and work with the system as a conductor. So in this case, our positive side is the chromel side, and the alumel side is our negative side. As that flows through, again, the device is going to be sensitive to the amount of current that's flowing through this thermocouple, and as the temperature changes, it's going to change the speed at which, or the amount of current, I should say, that flows through, and so it'll change. That's why we refer to it as a current-sensitive device. Again, a little bit more advanced as we start talking about this with a turbine engine as opposed to a reciprocating engine. Typically, when you have EGTs on a reciprocating engine, you'll have individual thermocouples that go to each individual stack that you're measuring EGT on. In some cases, you could measure EGT on every cylinder. In some cases, you may just measure EGT on your hottest running cylinder. Same thing goes for CHTs. These aren't really necessary per se on a reciprocating engine, but they're really nice information to have. And so a lot of times you may see a reciprocating engine that only has one cylinder head temperature gauge on it. It'll typically be one of the furthest back cylinders on the engine, so that you're basically watching your hottest cylinder as a reference to make sure you don't overheat the engine. When we're looking at a turbine engine, it's a little bit different in the fact that we measure in a number of different points in the turbine section to be able to get an accurate temperature reading on the entire thing. The only real point that I want you to see right here is these thermocouples are wired in parallel to each other, right? But in series through the two leads. So we have our alumel and our chromel side. And what we see right here, this entire section we could simplify kind of like this. It's going to be a weird drawing, but let's see if I can do it anyway. So if we have our green side for alumel, like so, there we go. And if we take our, boy, let's call that yellowish side for chromel, just like that, then all of these connectors that we have in between are going to be wired like this. Oops, that's the one I wanted. Going to be wired like this. That is an irritating feature, right? So as we go through, these are wired like so. So the leads are in parallel, but we still have a series circuit going from our positive side and around through our negative side. So that's what we're looking at.